and continue our lectures. Oh, before we continue, I have forgotten to tell you something very important. It is valid for the PN junction and also for the Schottky diet. For that purpose, just go back to the band diagram here. Yeah, exactly. Now, now here we are. Okay, so let's then go to the, oops, to the band diagram. That's on page 59. What does happen if you apply a little bit forward direction, forward bias? You elevate a little bit the conduction band edge. Well, and you increase the probability for the diffusion. Yeah. What happens if you increase this forward bias as much, perhaps you know what I will tell you now, as much as you have had the built-in voltage. So what happens if you increase this Fermi level that much that your conduction band gets flat? That's the flat band condition. The probability gets infinite. Yeah, exactly. It gets infinite. That means, theoretically, your current is infinite. So the internal diet, you can't apply higher values than the built-in voltage based on the assumptions we have to calculate this value. But which assumptions we have? We have some of them. Namely, we have the assumptions of weak injection. And which weak injection means your excess concentration you inject is much lower than the majority carrier concentration itself. So under these conditions, we have a limit, the flat band condition. And the flat band condition means your applied voltage would be so high that you get the flat band case. And this you can't reach at all. You know, the rest of the semiconductor is a resistor. So infinite current can't be transported through the semiconductor. So the external voltage is the sum of the resistor voltages, VR, and here also VR, and the voltage you have here internally applied. So the equivalent circuit of a diode is the diode itself and its parasitic resistances, and then you have the external node. Okay, so I wanted just to tell you that theoretically you can get a flat band condition, infinite current, but this never occurs. That's all what I wanted to tell you, and it's also valid for here. If you have the flat band here instead of not that flat, then you can pour out infinite number of electrons, and that's not possible. Okay, now let's go to the Zener diode, Zener diode. This Zener effect Do you pronounce it Zener or Zener? Zener. Zener. Yeah, okay. So the Zener effect is very interesting. Before we go to the Zener effect, we go to the symbol. Um, Compared to the previous symbol, this one is missing. Then we have a Zener diet. Okay, so it's proven to be sketched in a wrong way if you have a document. Just cross-check the text to the symbol, what it is meant. Okay, you often see this symbol and they mean Schottky. So don't be confused. So the Zener diet has a very special characteristic. In forward bias direction, so if you here plus to the P zone minus to the N zone, you are in the forward bias. So the Zener diet is a normal diet in the forward bias direction. But in the reverse bias direction, it is designed to have a certain breakdown voltage. It is by intention a certain value. Okay, so you have this also um, for for these diets. If you reverse bias, you get this one, and somehow you get breakdown. But this is not on design. This is a result of your characteristics you have had at least as a purpose to withstand. Let's say you would like to withstand 5 volt, then the Schottky diet withstands 6 volt or something like this, but it can vary. But if you buy Zener diet, it is the designed or at least picked from the production value. Okay, how it happens? Up to now, we have learned that if you reverse bias, then you calculate the electrical field. The maximum point is at the center, at the junction. And this, if you reach the critical electrical field, yeah, then your diode breaks down. And we have learned this breakdown appears there at the center, at the junction. And if you increase the volume where the electrical field is higher than the critical one, then the current increases. So the breakdown is not a destroying one. It just starts to increase. And what happens? The bonds are broken, the electrons and holes accelerate and uh, make an avalanche and break down additional electron hole pairs. This avalanche breakdown requires a certain electric field and yeah, it needs to additional knock out an additional electron from its bond. And this knocked out electron from the bond knocks out in the second one after it is accelerated. So braking and acceleration, braking, acceleration. This is the avalanche breakdown. If you now increase the temperature, then your collision partner is a moving target. That means the acceleration takes place, but the knocking out, the second one, is weakened. That means your avalanche current decreases with increasing temperature. That's the first effect. Decreased current with increased temperature. Or vice versa, increased voltage for breakdown. You need more electric field to get the moving target shoot up. The second effect in the Zener diet is, yeah, You know that you can go through the wall without making a hole into the wall. You can tunnel through the wall if you are so small like an electron. And if the wall's extension is comparable to the wavelength of the electron. So that's the tunneling effect. If you are small and the wall is thin enough, you can tunnel through the wall, potential wall. Okay, so we say that the electrons, let's go to the p-n junction. Yeah, yeah, here. We say that the electrons need to overcome the barrier to diffuse to this area. The second mechanism is if this width is small enough, then the electrons can tunnel straight through the wall. And that's very interesting. That's a tunneling current. And the tunneling current, you can say that if, one moment, if you are a moving electron, you have more kinetic energy. And then the wall gets more transparent for you because of your energy level, which is higher. That means the tunneling current increases, or other way around, the voltage to reach a certain tunneling current decreases. So you have two counteracting tendencies. The avalanche breakdown voltage, has a negative temperature coefficient. Increasing temperature, lower value. The tunneling current coefficient has a positive coefficient with increasing, oops, vice versa. The tunneling current you need with increasing temperature, lower voltages, and the avalanche you need for increasing temperature, higher voltages. Now, if you design your doping level that way that your these two coefficients just zero out, then you have a voltage source in breakdown direction. Then your voltage for your breakdown does not change as a function of the temperature. And that's the purpose. You generate with a Zener diode by doing the following thing. You reverse bias a Zener diode towards ground. You add additional resistor to a voltage source. And the value, let's say that's 10 volt. Your Zener voltage is 4.7 volt, let's say. You take here 1 kilo ohm, so that certain amount of current does flow. And the value, the breakdown value of 4.7 volt, if it is designed to 4.7, keeps constant and is not a function of the temperature. That's the purpose to use a Zener diode. Yeah, that's it. Voltage source. If you need a voltage value, you make it this way as the most simple way. The not simple way of generating a voltage not dependent on temperature is the so-called band gap, but that's in another lecture. That's in circuit design, but it is not lectured at the moment nowadays. But you have it in your lecture notes if you go to circuit design and download my German material for a band gap circuit. These values for a band gap changing of the voltage as a function of the temperature is a means of designing the increase of certain current, the decrease of certain current, adding them together, it's constant, and the result is a constant voltage. Just for curiosity, take a look there. From the device point of view, it is the Zener diode based on physics. Okay, so a single two-terminal device basics are over. Now we go to the next topic. The next topic is MOSFET. MOSFET is very simple, but understanding it, yeah, it takes energy. Let's say it this way around. Let's put some into these lectures as energy sink. MOSFET, metal oxide semiconductor. Metal oxide semiconductor. Here, metal oxide semiconductor. Field effect transistor. For sure, you know these abbreviations, but yeah, it's here. A MOSFET looks like this. If you saw through a wafer, just straight through a MOSFET, make a simplistic sketch, you get this image. So here is the wafer, a part of that. On top, you have your gate metal. The oxide in between has a certain thickness. Underneath this oxide, you have your silicon, a very low doped silicon. P minus, minus means low doped silicon. Plus means high doped silicon, P-type, boron. N means, yeah, donator doped, so phosphorus doped, highly. So these areas are ohmic contact areas. And this area is a functional area in the semiconductor. And you see now between source and semiconductor, P and semiconductor, metal. So we have here a resistor, here a resistor, and NP junction. What is an NP junction? That's a diode. In which direction? This one. And here we have an additional one. So we have two diodes, anti-parallel. So if you want to have the current this way through this diode is blocking it. So in this configuration, your MOSFET is switched off. No current is flowing, except the current which flows for the saturation value. This cannot be prevented, sure. Now, if you apply a positive voltage here and a negative voltage here, so plus, minus, you attract electrons to the interface. If you do that, your resistor is connected to this channel, and this resistor can connect it to the environment. So your channel is now populated with electrons. This behavior, how it is populated, with which value, and why this value is required to populate this channel with electrons. This is the topic for the next slides. To analyze this channel, we don't require the full device. We just need this cross section: metal, oxide, semiconductor. And this is also here: metal, oxide, semiconductor. And the band diagram of this area with this axis, we have here the x-axis. So from now on, if you see this band diagram, see here the gate, this gate, see here the oxide, and see here the p-type semiconductor. Okay. And this band itself, oh, there is one more person waiting in the waiting room. Hi, Herr Müllerschön. Just forgot you. Fortunately, we are recording our lectures. Oops, I have forgotten to start the recording. No, it's recorded. Just joking, Mr. Müllerschön. Um, well, we this don't worry. I've just overseen that you are waiting. Metal oxide semiconductor, and we have the flat band condition. That's for simplicity purposes, for sake of simplicity. What does that mean? At the beginning, all materials have a constant vacuum energy level. All materials. Material one is here, two is here. Vacuum level, it has the same energy. The Fermi level is a function of the work function. And if you assume, just assume, in reality they are slightly different, but if you assume they are equal, then the Fermi levels are aligned. Then the flat band condition is in the same time your thermodynamic equilibrium. So this band diagram is in equilibrium because we assume that the work functions are equal. Okay, now let's analyze all the lines in the band diagram. Okay, the vacuum level we have here. The metal has its Fermi level above the conduction band. Here we have the index Fermi level of the metal, conduction band edge of the metal. Let's go on with the semiconductor. Okay, S for the semiconductor. The intrinsic level is in the center of the band, of the silicon. So it's halfway to the between them. The Fermi level is close to the valence band because it's p-type. It's boron doped. And the difference between the intrinsic level and the Fermi level is the so-called VIF. You can calculate that because the center energy, it has this value, and the Fermi level energy has, as a function of the doping, a certain value. We have learned that. So we can calculate the VIF. And the additional value is here depicted. It's the electron affinity of the semiconductor. And the thickness of the oxide. So this dox is this dox. I hope now All of you are now synchronous to the content of this slide. What do we have now? We have 0 voltage across the oxide. Why? Because the Fermi levels need to be aligned in the thermodynamic equilibrium, and they are aligned because of these equal values. And if they are aligned, the vacuum level is constant. And if the vacuum level is constant, the voltage difference over the oxide is 0.1. Let's go on. What is the oxide capacitance? Okay, what is the capacitance itself? The capacitance itself is C is epsilon 0, epsilon r times A as an area divided by D. Yeah. And if you have C dash, then if you have C dash, then you have normalized for the area. So the area capacitance or sheet capacitance. So as we are not interested in the area itself, we just depict the oxide capacitance normalized to the area with the dash. Okay. And the VIF, yeah, you can take a look into your notes. You can calculate it and get it to this value. So the voltage is normalized by the charge. The energy is normalized by charge, the voltage. So the voltage between the intrinsic level and the Fermi level is a function of the doping level as a reference to the intrinsic charge carrier concentration. Okay, these are just facts. Now we start to play with these facts. In order to be able to play, we need the play rules. Okay, somebody has? Yes, please. Yeah. Okay. So, yeah, I understand. So you wonder about why they are different, why not everything is the same. First part, yeah, the first part, if this would be P minus, if, then we would not have here an ohmic contact. So in order to have an ohmic contact, we need a heavy doped area there. So consequently, the remaining question is why the substrate is not also P plus. And this is a very good question. This doping concentration, is a design value to set the threshold voltage. And this we will learn after 4 or 5 slides. And what is the threshold voltage? Therefore, very good question. What is the threshold voltage? It is the voltage after which you apply between gate and bulk, you get by definition a channel. That's the threshold voltage. Okay. But that's our aim of this lecture. This answer, don't forget it, will be, this question will be answered. Okay, not at all. We have now several possibilities to play around with this Venn diagram. We can pull up and pull down. So let's start with pulling up the metal or pulling down the semiconductor. Pulling down is plus, pulling up is minus. Okay, so if you apply a voltage between gate and bulk negatively, so the gate bulk voltage is smaller than zero. That means the left side is minus, the right side is plus. Exactly. Then we are in the so-called accumulation mode. Well, okay, what does that mean? Where does this voltage consumed in the semiconductor? Because if you have here a voltage in between, the voltage drops across the air. Where does the voltage drop in the MOS area? The voltage doesn't drop in the metal. We learned metal is the equipotential area. Yeah, exactly. Then, okay, what is oxide? Oxide is something isolating. So theoretically, if you would have here metal and here metal, then you would have a normal capacitor. So all voltage would drop over the oxide. But we have just only here metal, but here a semiconductor. And therefore, a portion of the potential difference is in the oxide, and a small portion is in the semiconductor. Why? In this band bending, the holes bubble up to the interface and accumulate there. In the accumulation mode, so go back to the structure, if you have here more holes, it doesn't help because you have here N, P, N. You keep up having anti-parallel diodes. Therefore, accumulation mode is just for explanation purposes useful, but not for working purposes. Let's explain here our capacitor. What does a capacitor, a plate capacitor, have? That's your plate capacitor. It has the same Q on both sides. Electrical engineering, first semester. Mr. Boca, wake up, please. Take a coffee. Sorry for disturbing. Yeah, I know. This is fucking dry topic, so therefore I need some liquid. A plate capacitor stores the same charge on both plates, but with different signs, opposite signs. Okay, so the metal stores electrons and expects in the semiconductor some positive charges. But the overall value, so if you start to count these holes, so if you start to integrate, then the Q's are equal. Keep this in mind all over the next slides. Important. The charge is same. Yeah, sure. You start your lecture time in bachelor, first semester, electrical field, capacitors are explained. Q plus is equal to Q minus. I say the same in the MOSFET. But now we have a semiconductor. That's the only difference. Let's continue. Now we are going into the right direction. Depletion mode. Your gate voltage is larger potential than the base potential. Base, bulk, sorry. So the plus sign is at the metal, the minus sign is at the semiconductor. Now your applied voltage, the full applied voltage, is the potential difference in the oxide and in the semiconductor. And again, the charge in the metal is same like the charge in the semiconductor. But who is giving you this charge? It is the space charge region, the depletion region. So the depletion region is providing you the charge you need from the semiconductor side, and the metal is providing you the positive charge Q plus and semiconductor Q minus. And this Q is stored in this capacitor. That's all. The only difference to the metal capacitor is that in order to be able to store a Q minus charge, you need your doping concentration and the width. You increase the width, you increase the charge in the space, and the opposite one is accumulated just at the interface. And therefore, in the semiconductor, I have to draw a box because you have an extension, a physical extension into the semiconductor. No, this way? Yes, the physical. Okay, here's the limit of my picture. I have to increase my picture. One moment, please. I have to play now. Mwah. So, um, here, this extension of the space charge and this space charge accumulation represents here. Now I'm a weather frog. Here you have then the charge in the semiconductor, and the corresponding positive charge is assumed to be in an infinite layer in the metal. Okay, now I can reduce my size. It's frightening. Okay, now I have the right size again. Oh, a little bit bigger. It's too small. Well, now it's good. You calculate it by the space charge extension, by the doping concentration, and by the value of the charges. So if you have a p-type semiconductor, you have boron, and boron is, no, yes, it's boron, and boron has accepts one electron and is one times charged positively, negatively. Therefore, this minus sign. Therefore, the box at the lower side. Here is negative, here is positive, and here is 0. Okay. What we can see here is now all these qualitative statements. The oxide voltage is the charge on the capacitor. The surface potential, so the potential in the semiconductor, is defined by the width of the space charge. Okay, and the width of the space charge, yeah, we know this equation from all our lecture slides before. It is square root dependent on the voltage. Here we have it again. So therefore, the charge is proportional to the square root of the potential. So the charge in the semiconductor is proportional to the width, sure, You double the width, you double the content, sure. And the width is proportional to the square root of the surface potential. So here we are. So the charge bound to the lattice, so therefore B, y bound, because it's here bound, it's not movable, therefore bound to the lattice, defines the charge, and this charge defines the voltage, and the sum of these two voltages is your voltage. Okay, that's enough for this slide. Now it gets more interesting, slightly. What we have done, we have increased, one second, here you see a certain voltage difference, your voltage. Now, this voltage is increased. How much? That much that your surface potential, that much that your band bending is larger than VIF. Take yourself a closer look to here. Your conduction band edge, valence band edge, and your Fermi level. Due to your applied voltage, you need some charges. This charge, you know, Poisson equation, blah, 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 makes band bending. Band bending as much that it is larger than this difference. Okay. If this is the case, then your intrinsic level crosses your Fermi level. And if this happens, then your Fermi level, no, here is the Fermi level, EF, is closer to the conduction band edge. In the bulk, it is closer to the valence band edge, but at the interface, it is closer to the conduction band edge. What does that mean? What is a semiconductor? It's a sketch. You don't have to do this. If you have this Fermi level, you say this semiconductor is N-type. If you have a Fermi level which is closer to the valence band edge, then you consider that's a P-type. Now you change by applying a voltage. You change this behavior of the semiconductor at the band, at the interface, just here. That way that you accumulate electrons. You accumulate electrons at the interface. Like you would have doped it N-type. But you don't change the doping. You just change the potential. That's it. You change the potential. The Fermi level crosses, intrinsic level crosses the Fermi level, and the interface gets N-type. You start to have an inversion charge density. The inversion charge means you expect holes, you get electrons. Inversion. But just at the interface. Okay, point one we have. Now, in the sketch, you see that your space charges are this box. I will go in and say, so this charge portion, so if you count this area, you get the charge due to the space charge, and this additional electron accumulation is this portion, this small portion. So it's negligible, but it's there. Now, what happens? Now we get, that's the most important slide for the MOSFET. Print it out on A0 and pin it to the wall. No, you don't have to do that. It's a nightmare, but you need the content. You define that the surface potential is equal to 2 times VIF. You define it. And then you say, if you have a surface potential that much, that it is 2 times the VIF, then you have a starke inversion. Yes, sure. Strong inversion is compatible. Strong inversion. Okay? What that it means will be explained now. But now, just the definition. The bending at the surface is 2 times the value between intrinsic level and the thermal level. And if this occurs, you have a strong inversion. Now, what does that mean? It's very simple. If the bending is 2 times this distance, then your intrinsic level is bent 1 time, then your intrinsic level is equal to the Fermi level. And if it is bent 2 times, then your new VIF is exactly as large as your initial VIF, but vice versa. That means that at the interface, your carrier concentration for electrons at the interface is equal to the carrier concentration of the holes in the bulk. Once more, Fermi level in the vicinity of valence band. If now the Fermi level with this distance is now here with this same distance, then this electron concentration would be the same like the hole concentration. And exactly this happens at the oxide semiconductor interface. The conduction band Fermi distance is the same like the Fermi valence band distance. And this, I have put it here. So the electron concentration in the p zone is now defined by this equation. This is a general equation. If you put into the general equation your biasing, your potential, 2 times VIF, then the resulting value is the same like we have had for the p doping. If we have a p doping, we have this equation. Now we have with 2 times doping the same value for the electrons. Okay. And this happens because these distances are equal. And this equation is a definition for strong inversion. And this means now the following. Now let's go to the charges. Your space charge has a certain concentration, okay? And your inversion charge has the same concentration on top. Therefore, this value is defined as the strong inversion. But if you apply this voltage across bulk and gate, you have generated an N-type semiconductor at the interface, but the amount of charges, so if you start to count them here, so what does that mean? If you start to integrate this area, it is almost zero compared to the rest. That means if you apply this inversion voltage for strong inversion, you reach the threshold voltage. If you reach the threshold voltage, you have at the interface as high a concentration for electrons as you have in the bulk of your semiconductor as holes. But their amount is negligible. The density is inverted, but the amount is negligible. That means if you buy a transistor, look into the application sheet, and in the application sheet you see for a power MOSFET, your threshold voltage is 5 volt, 4 volt. If you apply 4 volt and you expect current, you will see nothing. The current is very, very low. That's the starting point, by definition, of the current. If you want to have a realistic amount of current, you have now to populate this area. How you do that? You don't apply the threshold voltage, you apply more. Now it gets to be interesting. Let's first calculate the threshold voltage itself. Now we keep on having this inversion, strong inversion. If we know by definition this potential, what we know in addition? If we know this potential, we know the charge in the space. Why we know the charge in the space? Because this additional charge by inversion, we say it's negligible, and we know by this equation how wide the space charge is if this potential has a certain value. And we know now which the value is, or which value we have, what value it is here, bad English. The value for the bending is 2 times VIF. And VIF is, now we come back to your question, Mr. Rauscher. It is defined by, the VIF is defined by the doping level. So we take one arbitrary doping level. We have one arbitrary VIF, intrinsic Fermi distance. If we have this arbitrary Fermi intrinsic distance, we have for sure the value for 2 VIF. It's times 2. And this is the potential on in the semiconductor. If we know this potential in the semiconductor, we know the width of the space charge. If we know the width of the space charge, we know the charge itself. If we know the charge, we know to which value we have to charge the oxide, with which voltage we have to charge the oxide capacitance. Because the oxide capacitance itself, the oxide capacitance itself, 1 second, please. Let's go back to the almost first equation. Oxide capacitance, what is a capacitance? Capacitance is Q divided by V. If we know the capacitance, if we know the voltage, if we know the charge and the capacitance, we know the voltage. Now we know everything. Now I will repeat all these facts on this slide. We define this as strong inversion. By this definition, we know this extension of the space charge. With this extension, we know the amount of charge. If we know the amount of charge, we know to which voltage this capacitor is charged. So we know this voltage because the second one we defined. Therefore, we know the overall voltage. And this is the threshold voltage. The threshold voltage is the defined gate bulk voltage, which has the oxide voltage and the defined surface potential with 2 IF. If we put together all these equations, we end up with this equation. And now let's go to, again, the spreadsheet. In the spreadsheet, we have for sure also all these equations. So I defined the oxide thickness to be 7. I defined the oxide thickness to be 7 nanometer. The relative dielectric constant of the silicon oxide is 3.9. I said that the doping level is 2 times 10 to the power of 16, like for our diode. Then, as a resulting value, we have 5 microfarad per square centimeter, quite low value. The VIF is 0.365. It's calculated by this equation, like in the lecture. So that means the bending, one moment, that means that this bending is 2 times, one moment, 0.365 volt with the given physical values in the spreadsheet. Now we are going back to the spreadsheet. So the extension of the space charge region is 217 nanometers, very low value. And the resulting threshold voltage, is 0.745 volts. That's a realistic value for realistic semiconductor values. Now I get again back to you, Mr. Rauscher. Now I'm changing the doping concentration. Here we are. I'm changing the doping concentration. I will change it. I will have to change it somewhere else. It is N11. Okay. N11 is where we have had in the diet area. So let's go to the diet area. N11. So I have taken the value where we have put in the diet values. So I make it unrealistic large. Just one more zero, okay? It's 2 times 10 to the power of 17. Oh, no, it needs to, yeah, you're right. So back again, and here one more. So the acceptor doping is now 10 times higher. Or let's go back to the threshold voltage of the MOSFET. You see? 0.9 volt. If you increase your doping level to a value which is closer to the ohmic contact, it's 10 to the power of 19, you cannot switch on the MOSFET. That's the reason. That's the only reason for having it low. Okay. Um, what we have now in addition is blah blah blah. Fall off. Okay, I go back to the initial value. Zack. Und zack. Und nochmal zurück. Okay, now we have the original values. Now I want you to give me your opinion, your professional guess. What happens first from your stomach? What happens if we increase the oxide thickness? Don't take a look into the equations. What do you think? And try to explain your guess. Just try. Can be wrong, but just try. Be active. Mhm. Yes. And what is the result to the threshold voltage? Do you need more voltage or less voltage? Hmm? Exactly. Because what is the definition for the threshold? A certain VIF times 2. So the threshold voltage is the charge you need in the semiconductor. So I translate. That's very important. I will go back now to the slide, and then I will go back to you, Mr. Potter. Yeah, so I translate this voltage for the threshold. I translate this voltage to a width and this width to this charge. Okay, so giving the definition for the threshold voltage directly has the consequence that you store a certain amount of charge. From this point, your answer is absolutely correct. If you want to store a charge on a capacitor which has a larger distance, you need more voltage. You need more voltage. That's it. Good guess. So this type of thinking is the type which I expect to be answered in the oral examination. No equations. but the link of the mechanisms and the proportionality of the mechanisms, and not this equation itself. Okay, very important. And this equation reflects everything we have learned, for sure. It needs to have, it's just mathematics. The threshold voltage consists of 2 times VIF, for sure, because the full voltage consists 2 VIF, and it consists of the required oxide voltage. The required oxide voltage is a function of the charge, and the charge is a function of the space charge width. And therefore, we have this square root of the same voltage. Okay, so we have the VIF because it's just in series connection of the surface potential and the oxide voltage. And the oxide voltage is a function of the Q, and this is the Q. That's it. So now we learned how we can calculate the threshold voltage. So for the sake of simplicity, we assume that only for larger values than the threshold voltage, we assume that the channel is formed. But in reality, we have at the threshold some amount of inversion charge, but low. And also very low values for reverse biasing generates inversion charge. And XFAB technology in Germany, which provides the foundry process for the master students in our electrical electronics and drives center. It's no more Robert Bosch, it's electronics and drives center. This XFAB technology has a certain model which uses this charge to make circuits. Why you use this low amount of charge to make circuits? To make circuits which are very low power, microwatt, nanoampere electronics. Therefore, you can use this charge, but for microprocessor topics, you usually go above the threshold voltage. For us, the transistor is off for lower voltages than the threshold voltage and starts to conduct for higher values. What does that mean? This. It means this. What does that mean? This. Exactly. It means the following. We charge up this capacitor. We charge up with this capacitor. This charge is sum of the charge of the space charge region and inversion charge. Okay, and the other is from the metal. Yeah, the metal says you get what you need. Therefore, in the metal, I say I get my charge, and in the semiconductor, I get only one portion of the charge by the space charge region bound to the lattice, and the rest is provided by the inversion layer. And the inversion layer, now we go back to the proportionalities. Therefore, I have hammered on the proportionalities. This space charge region, this Q in the space charge region is proportional to the square root of the surface potential. So if you plot the potential and the charge, the space charge region, yeah, square root behavior. What is the behavior of the inversion charge? What is the behavior if this distance gets close? If this distance gets closer, it's Boltzmann statistics. It's exponential. That means the Qi makes this. And this means if your space charge doesn't increase so much, you settle down the complexity and say the space charge region doesn't increase anymore. If you need more Q, you get it by the inversion charge because the inversion charge increases exponentially. And then you can easily calculate your channel concentration. And the channel concentration is then defined by Qi. Okay, so that means if you have excess voltage more than the threshold voltage, then your concentration increases exponentially and the oxide and the space charge doesn't increase exponentially, it's increased by the square root of this potential. Therefore, we assume that this box is constant and all the rest is coming from here. And coming from here means, yeah, that we have now following condition. We go back one step and say, channel, one moment, is the channel present on? Yes. Then the voltage you apply, you take out the threshold voltage because to form the channel, you need this distance here. So 2 VIF, you need to form the channel. And after forming the channel, you can generate the inversion charge. And the inversion charge is generated by the overdrive voltage. You drive more than required, and the voltage which is more than required applied generates Qi. So you switch on the channel. That's it. And switching on is the threshold voltage. And if you apply more voltage than you require, you overdrive the gate, and the overdrive value is the charge you get into the channel. That's it. That's the MOSFET. So it's not complicated. It is a lot of information in one chain. And this is what I wanted to transfer to you, this chain, once in a life. So that you can say, I have understand that fucking MOSFET. And in your transistor model, there is a value VIF. You know where it comes from. There is a value Na. It's the doping concentration, Mr. Rauscher, of the bulk. So you can design your own MOSFET. That's it for today. I think we will see us next week and continue with all the rest of the slides with the MOSFET. It will be not a less amount, but less length of the chain. So the longest chain in the action was for the MOSFET, the most complicated one. So take your time, go through the slides, write down your questions, and drop me next week, please. Okay? Not at all. See you next week. Bye bye. Thank you. You too. Bye bye. Yes? Okay. Can you go at the moment to YouTube? Okay, then I will go. One moment. One moment, sir. I one. So one moment, please. Here we are. Virtual freigeben. So here you see uh, my videos, and I also uploaded the video from today, the first one. During the lunchtime, it has happened. Yeah. Yeah. Everything is okay. So then let's see us again next week. Bye bye.